Hey, how are you? Hello, welcome back. My voice is doing better. I just took a very long nap, and let's well, before we get back to this mathematics, let's talk about uh, appetizer stuff. Okay. Um, all right. Yeah. We talked about women, right? Women are very emotional. They are not logical at all. They are very inconsistent. Okay, so women, one time they hate sex, some other time they love sex. Okay, it depends on their mood, I guess. Right? Yeah, we guys, we are always consistent, right? We always love sex, but women, they are not like us. They hate sex and they love sex, whatever. And even if they enjoyed sex, later on they may regret it. Yeah, women, that's how they are. They're inconsistent. Uh, how do I know? Well, women being inconsistent, I think I heard that in Twilight Zone series, I think. Okay? It's just very well known saying. Okay, now, let's talk about child of ultra interracialism. Okay, let's say, yeah, like the children of Marco Rubio, children of Ted Cruz, children of Ivanka Trump, Jared Kushner, children of Bruce Lee, children of Tiger Woods, all these ethnic guys who married the most beautiful white girls, which is disgusting. But they're children. I mean, they are not to be faulted because they're not to blame. The children of ultra interracialism because it's not their fault. It's the yeah. Also, Barack Obama, President Barack Obama, child of ultra interracialistic marriage, illegitimate marriage, immoral marriage. Okay, yeah, President Obama's mother, I think she's a very beautiful white girl. Okay, his father, yeah, black guy. Okay, he's not even African American guy. He's just African guy. Okay, very greedy and lustful. So yeah, their parents did something sinful and immoral. Okay, because they were possessed by ultra interracialism, right? So the child is now born. They are not white. They are ethnic. Okay, so those white girls who marry beautiful young white girls who marry uh, ethnic men, they are they just kill themselves. Okay, it's suicidal. It's racial suicide. The ultra interracial marriage is a racial suicide. It's a and also for those guys, ethnic men who marry young white, beautiful, slender girls, yeah, they're genociders. Okay, they commit micro genocide. They are killing white race by marrying them. Okay, that's what they're doing. Okay, so they don't know what they're doing. Okay, because they don't know. Nobody taught them. They think it's okay, but it's not okay. All right, it's something satanic. They don't know. Nobody taught them. So I'm teaching you. I'm telling you guys. Okay. Well, I have three drinks. It's so beautiful, right? Diet soda, water, cranberry, diet cranberry. Fantastic. So, but children, they are not to be blamed. I mean, they didn't do anything wrong. They're innocent, and they are all beautiful. Okay, they are all beautiful. Okay, but the parents they did something very wrong. Both of them. Okay, they shouldn't have married. Okay, we need to stop or put a stop on all this evil. Okay, ultra interracialism. It's something extremely heinously satanic. Okay, tattoo piercism, yeah, it's bad. Ultra interracialism, well, it's the worst. I think it's worse than gayism even. Okay, because it is satanic. Okay, an ethnic man killing white race. Ethnic man killing white race. Okay? Wiping out the white race. That's Marco Rubio, Ted Cruz, Jared Kushner, and the motherfucker that's who's fucking Tiffany Trump right now. Okay? Yeah, the Jews, Hispanics, or Bruce Lee, like Asian, or yeah, the what, Tiger Woods, yeah, they're all the same. Or Clint Eastwood even. Why? Because he's too old to have kids. And why are you? Why did you marry a beautiful young white girl? And he's wasting her eggs. I mean, they're not having any kids. Clint Eastwood, he's just too old to have kids. So he married a beautiful young white girl. Now her gene, her eggs is now wasted away. Okay? Yeah, it's ultra interracialism. Okay? Even though Clint Eastwood is a white guy. Doesn't matter. Okay? And even if a young man, young white man, marries a beautiful young white girl and they never have kids, that's ultra interracialism too. Because you're wasting white girls' eggs, white beauty gene. Okay? You cannot do that. Beautiful young white girl must have purely white babies to preserve that beauty. I look at white people, aren't they beautiful? Of course they are beautiful. Come on, get a grip. Yeah, stop lying to yourself. Okay, you don't have to be jealous. Just appreciate. Okay, I'm not white either. Why can't you appreciate other race? Why can't you appreciate white race? Huh? Don't get jealous. Yeah, appreciate other races. Aren't black people beautiful? Oh, they are gorgeous. Black people, both men and women, they're very, very beautiful people. Okay? I mean, as long as they're not obese. Okay? Yeah, anybody, no matter what race you are, you can be very beautiful. Tattoo free, piercing free, obesity free. Okay? Then you can be beautiful. Okay? Race, age is not a factor. Alright? Okay. I just want you to be healthy, okay? You're all beautiful, okay? Are you obese? Yeah, you're all beautiful, okay? But you need to be healthy. You need to diet, exercise, okay? That is so important. Alright? I'm sorry if I'm offending you, but I'm offending you so that you get better. I'm telling you all this on your behalf, okay? What do I get from saying all this? I get hatred, okay? Oh man, yeah, I'm sacrificing myself for you, just like Jesus did. Okay, I follow his footsteps. Okay, so now Jesus said, yeah, what you do with the left hand, do not let right hand know. And I kind of do that. It depends on the situation. Okay, if I did something very good did, I tell my superiors, yeah, I did this good thing because I take it as a leverage. Or sometimes I don't tell them what I did very good, but I can tell them when it comes necessary, when I need some leverage. So I store my leverage, then later you reveal it. Yeah, sometimes I do that too, okay? Or sometimes I don't tell them at all. Why? It all depends on the situation, okay? Like what I'm doing here, the humanology series. Not many people know about it. A few of my friends do know. I guess they Googled my name or something. They found out, okay? Always a few friends of mine, they even found out about my novel. And I was like, oh my goodness, how did they find it? I didn't use my real name, I used my pen name. But somehow they found out. So that's fine, but I even with friends who know about this human knowledge series or my novels, we never talk about it. Why? Because I don't want to talk about it. Okay, to me this is, oh my goodness, I've been showing my bald spot all this time. Sorry, because to me this human knowledge series is like a public secret. Okay, I don't want to talk about it. Even my presidential candidacy is a public secret. Okay, people know about it because I used to tell them, but I don't talk about it anymore. I rather not. Okay, because it's just unnecessary. I don't talk about it. It's like my private life, private public life, whatever, however you characterize it. Okay. Well, my hair is getting more interesting. It looks like a sun or lion, whatever. I like it. as long as my both part is covered. It's funny. Woo! I like it. Uh, so yeah, that's that. Okay, so I guess we can take a break and get back to this mathematics. This mathematics is like, do you like classical music? I love classical music, by the way. Mathematics, it's kind of like background classical music, because I mean, it's like background classical music. Yeah, it's cool, okay, but it's something we do in the background because the main meat is humanology, right? Because mathematics is kind of boring, boring thing to do. We take a break from it and we talk about humanology. That's the real fun stuff, the human world. Who care about these numbers and stuff? Okay, classical music. Some of them are really exciting, and other classical music is cool because it's kind of boring. Okay, two kinds: good, like exciting classical music, and some other kind of nice to have in the background because it's not so exciting. Some of those other classical music, that's why it's cool. It's a nice background when you study, when you read a book, because it doesn't grab your attention. Okay, so yeah, either kind, exciting and not so exciting classical music, they're both cool. They're different uses. Okay, so that's what we do with mathematics. It's not very exciting, but it's a nice background to have, right? So that every now and then we have very good excitement talking about humanology. Okay, so mathematics, nice background. Okay, kind of boring, only not so exciting background. Okay, so we will continue. Okay, okay, let's take a break. So, uh, All right, we are back. Let's briefly talk about some other stuff. So, every culture, like Japan, Korea, China, or Pacific Islands, South America, Europe, Africa, Pacific Islands, Micronesia, Indonesia, Australia, whatever culture, like native culture, right? They have fantastic stories. Old stories, like traditional stories. Oh, they are treasures. We need to preserve that. Like Alaskans, Hawaiians, Eskimos, whoever. Yeah, they have fantastic stories, like oral tradition. Oh my goodness, so cool. I was in, I went to a gas station to buy cigarettes, and I listened to this classical music channel on the radio, and there was this wonderful storytelling time. So, but Japanese story, traditional, old story. It's a 1 inch boy, okay, small 1 inch boy, and he wanted to be a samurai. Okay, it's kind of like Cinderella story, and it's like it's all of us, right? We are underdogs. We want to evolve to the higher level, and that's cool. That's a good thing. I want you to be successful. Don't be like me. Okay, I'm a failure. I'm a total loser. Okay, I want you to be more successful than me. Because will I ever become a president? Yeah, so it's like Cinderella story. We all have that kind of dream, and it's a good thing. Yeah, be ambitious. Have a dream, go for it. I'm a registered candidate, so I'm like this 1 inch boy, very small boy who wanted to become a samurai, soldier, warrior. So story goes like, so I had to look it up because I had to go to the gas station and the story was over in the radio. I bought some sandwiches and hot dogs and yeah, I grabbed a pack of mayonnaise too. Okay, I even have mayonnaise in the freezer, in the fridge refrigerator. Every now and then, the sandwich I purchased, yeah, it has cheese in there. Do I de-cheese it? No, I eat it. Why? Because it happens only like once, less than once in a blue moon. Maybe 3 times a year. I don't know. Once a quarter, I guess. I think that's fine. Sugar and fat every now and then is fine. Okay? Just don't do it every day or every week. Do it less than once a month. Don't even do it every other month. Do it like once a quarter. Okay. Our body does not need fat. Why? Because our body can synthesize fat. Fat, carbs, protein, chemically they don't have too much difference in their structure or composition. Okay, it's mostly carbons. Okay, building block of life, carbon. Okay, carbon is not a bad thing. It's a good thing. We are made with carbons mostly. Yeah, CHO. Okay, carbon, water. That's or nitrogen. Okay, it's just our body. Okay. Oh, it's getting cold, man. Oh boy, I gotta put some more clothing. Oh boy. So yeah, this 1 inch boy, what happens was he was adopted by this old couple who do not have any children, and so the this 1 inch boy left his parents. So yeah, he didn't grow up. He just stayed 1 inch. I guess he became a teenager, but he was still 1 inch. That's the beauty of the story. It's like I kind of identified myself with that 1 inch boy because I'm not quite growing up. I mean, yeah, I grew up a lot in knowledge internally, but in terms of my the money I'm making or social status. I'm 40 years old and it's just staying the same. I'm making average American salary, $50,000 a year. I mean, my colleagues who went to school with me, they are making at least twice as much, okay, nowadays. Why? And their school grade was less than mine. Okay, I had better GPA. Okay, but they are making at least twice as much as I do. Okay, me, I'm not making any progress in that venue, but because my focus of life is knowledge, wisdom, character, ethics, morality. Okay, finding the truth. In a way, I live like Jesus did. Okay, self-sacrifice. Okay, my life is kind of like life of crucifixion, kind of. That's what I aspire to be. He's my role model. I try to follow his footsteps, Jesus. Okay, so okay, back to the Japanese story. So yeah, he never grew up. Okay, he stayed 1 inch, and then he left. Probably after he became teenager or whatnot, he um, I'm getting cold. We'll continue this in a second. Sorry. Uh, I guess I will have some hot water. I'm gonna uh, microwave this water. Okay. Dude. So this 1 inch boy never grew up. I guess he became 18 or something. So he left his adopted parents and went to the capital city of Japan and to become a samurai warrior. And then he got employment and as a small thing, right? Somehow, yeah, I guess some people were charitable, and so he got a job, and then there was this monster, kind of magical monster, sorcerer, I guess, kidnapped his employer's daughter. So he went to rescue his employer's daughter, and the monster ate him, swallowed him up. But this 1 inch boy didn't die. What did he do? He started poking the stomach in lining of this monster. So monster said, "Oh, stop doing it. It's hurt. It hurts." And he vomited out the young, I mean small, 1 inch boy. And he dropped his sorcerer's wand when he was fleeing away. The monster was running away. And so the 1 inch boy used the magic wand that this monster left behind, and he became a big man, regular size, regular height man. And then he married the girl he rescued, employer's daughter, and they lived happily ever after. Okay, yes, fantastic story. So, um, yeah, probably I never become anything. Okay, just like this 1 inch boy who never grew up. Yeah, but it ends in a happy ending story like Cinderella, Little Mermaid, Rapunzel. Yeah, it's all from probably from Grimm's fairy tale, right? It always have happy ending, fairy tale kind of. It's very inspirational stuff. All these traditional tales because it's about ambition, overcoming the adversity, starting as an underdog. It's everybody's story actually, okay? And we like that story because it resonates with us. It's, we have aspiration, ambition, okay? Me, I don't really care if I ever become president or ever become big, famous. I'd like to, but even if it doesn't happen, that's fine with me. Okay. So I'm having fun doing this. So yeah, but it'd be nice if it happens. If this become famous before I die, it'd be nice. It'd be nice. It'd be a nice change. It can happen. Who knows? Okay, but I'm not gonna push for it. Okay, so because I'm busy doing this. Okay, to me that's enough service to humanity and having fun. That's enough for me. Okay, but I want you to be more successful than me. Okay, because I'm in a way I'm a success because I'm discovering a lot of good stuff here. But in some other way, um, I'm really underachiever. Okay, in terms of money and social status, yeah, I'm very underachiever. But in terms of knowledge, wisdom, I'm an overachiever. I'm overachieving in this anyway. Okay, so we are creating brand new science here. Okay, that's something really cool. Okay, to me that's more important. Okay, okay, yeah. So I'm satisfied. Okay, I'm very satisfied. How my life has because I always wanted to do this. You know, humanology, creation of new science. I've been wanting to do this for a very long time, more than 2 decades. Okay, and I got it. Okay, God gave it to me, and it took a long time, but we got it. Oh, and we're also making it. Okay, so that's good. All right. Okay, let's get back to this argmax. Okay. Oh boy. Yeah. So women, yeah, they never make it easy for you, right? Actually, they make it difficult for you. Why? They don't give you an answer. If you have a girlfriend or dating or have a wife, you probably know what I'm talking about. Women like torturing guys by being silent, by not telling the guy what she wants. That's how women are. Yeah, they're like torturing men like that. It's a copium transfer, okay? Yeah, they don't tell guys what they want. They want guys to figure it out. They don't make it easy to guys. They make it very difficult for guys. It's copium transfer, okay? Yeah, it's torturing men. Like enjoying watching the men suffer. It's just the way it is, okay? It's the price they exact, they demand. Oh yeah, I'm gonna, I give you my body, so you're gonna pay for it, okay? By being silent, by not telling guys what they want, lack of communication, that kind of stuff, okay? Oh, this hot water is good. So how do I know? Well, I used to date, okay, back in the days. Ah, it's good. Let's take another break, okay? We'll be back. We will be back. Okay, well, I have hot water, so why don't I put some tea in there so that I don't drink vodka all the time because vodka is cool, but my liver probably needs some break. Needs to take a break. So, non-caffeine chamomile tea. Yeah, just try something new. I have tea, non-caffeine tea because yeah, diet soda. Yeah, it does have caffeine in there, but I like it so much. So I want to sleep at night, so I don't drink coffee. I used to. Then I drank coffee too much. It started to dehydrate me. So I had like constipation. Oh my goodness. So I don't drink coffee anymore. Okay, so it's nice. Hmm. It's good. It's good. Okay. Okay, so we have this argument. We'll get back to that. Hmm. Okay, so it poops out these two vectors basically out of n vectors. Okay, now what? I don't know. I guess we have to add them up, right? Because we are interested in formulating a generic formula of this stress vector summation. Okay, it's different from regular vector summation. Okay, if somebody is pushing me from either side, from left and right, I feel the pressure I'm feeling is doubled. Okay, so we have to add them up. If somebody pulling me apart, we have to add them up. Now that's negative pressure. They are both painful. Somebody pushing you, pulling you, yeah, it's both painful. Okay. By the way, let's talk about bullying. Huh? Uh, you see how beneficial studying mathematics is? Because we get bored, we don't want to quite do this. So yeah, we go off tangent, and I mean it's kind of mathematical term, tangent. We go off the tangent and we talk about exciting stuff like humanology, Buddhism. Is it exciting topic? I think so. I think it's one topic to talk about. It's always evil that excites us. That's why God created evil stuff like bullyism. Yeah, it's something very bad and evil. Okay, but it's interesting to talk about. Okay, yeah, all this evil stuff. So when I was a kid, yeah, I was bullied and was bullied. It's just playing around. Okay, it's just horse playing, young and dumb. People, young boys doing stupid shit like that. No big deal. Okay. So when I was bullied, so I was bullied and also I was bullied and I also bullied other people when I was a young kid. Okay. Uh, that's just life, isn't it? I mean, as an adult, don't you get bullied and bully? It's just the way. It's copium predation, okay? The copium transfer. That's all it is, okay? It's just way of life. It's just how it is. Now, but when I was bullied as a child, I took advantage of that. I started learning martial arts, okay? And also started to study very hard, okay? So that I gain more power, and I did. Okay. Yeah, you can take no matter what adversity there is. Yeah, you should take advantage of that. Okay. I mean, even look at gay people. They used to be bullied, right? But now they took advantage of that, and so they kind of rose from ashes. Gays, LGBT people, right? Yeah, political activism. Now look at them. They are the bullies now. They're extremely powerful. group of people. Okay. Yeah, it's nothing. I'm not. We are not trying to learn from them. No, no. It's like that everywhere. Any minority group, whatever. Yeah, powerless later become powerful. It's pendulum. It's governing principle, whether it's evil ideology or good ideology. It just works that way. That's just how it is. Okay. It's a natural law, a descriptive law. Okay. Minuplocism. Okay. Right? Yeah. Ideology. You suffer and then you get rewarded later. Okay. It's like that. Whether this ideology is sound ideology or evil ideology, it doesn't matter. It just that's just how it works. Okay. Okay. All right. Yeah. Pendulum, sinusoidal rhythm, sine curve, same thing. Okay. Now I'm kind of getting overheated now, so I have to turn off the heater. I know. I'm sorry. It's annoying, right? Yeah. Well, I get annoyed by myself too, but it's something I just cannot control. I'm very sensitive about temperature. Okay. I don't adjust to different temperature very well. Okay. I put on coat, take it off, probably 100 times a day. Okay. Uh, oh yeah, bullyism. Yeah, we talked about it, right? So yeah, it's just you want to be someone very powerful. Okay, to study very well. Also, you should know martial arts. Then it will all go away. You know. Yeah. Uh, let's get back to this. Okay. So we did take enough break. Um, if somebody pushes me and somebody pulls me, okay, then that cancels out. In terms of F equal ma acceleration, yeah, it doubles, right? But in terms of pressure, it zeroes out. So the stress vector calculation of this stress on a rigid body, it kind of works opposite way of traditional vector. Okay, so that's why we have to come up with brand new mathematics and brand new operator. Okay, to calculate stress because we are not satisfied with this Cauchy stress tensor concept. Well, first of all, I don't know much about it because I don't know much about tensors. I just know superficially. Okay. If I have more time, yeah, I'd like to study a little bit more. Okay, but the way he formulated Cauchy, stress tensor, I wasn't quite satisfied with his model, mathematical model. Okay. Just like I wasn't satisfied with the Alfred Marshall's demand supply curve. Okay, so we had come up with new transactional demand theory, right? Which is, as far as I know, is correct. Okay, demand supply curve, that's incorrect. As far as I know. Okay. And we don't care. Yeah, it's like monster, right? This big thing. Transact this what supply demand curve out. That's a huge thing in economics, right? For more than a century, right? But it's wrong. Yeah, there so many people who learn that shit and believe in that stuff, but we don't care. Okay, it's wrong. I mean, look at gay marriage. It's big thing, huge monster, right? But it's wrong. Okay, guess what? It's wrong. So then many people can be wrong. Yes. I mean, look at Nazi Germany. Hitler. He got majoritarian support from Germans. Germans are very smart people. I Immanuel Kant, Arthur Schopenhauer, all these classical musicians like Bach. I'm not sure if they're Austrians or Germans, but yeah, you know Germany, like Leibniz, Euler. I'm not sure he's German, but yeah, I mean Gauss, Friedrich Gauss, like Friedrich Nietzsche. Germans, okay, German. We're talking about some of the smartest people, Germans, and majority of Germans voted for Adolf Hitler. Okay, so yeah, huge number of people, very smart people, they can be wrong sometimes. Not always, but sometimes they do. Okay, they make misjudgment. Yeah, gay marriage, tattoo piercing, sugar fetishism, plastic surgeryism, marijuanaism. Okay, people who subscribe to those wrong ideologies, they are not stupid people. No, and it's not just a handful of people. No, it's majoritarian Americans. Americans are very smart people. As far as I know, I think Americans are very smart people, but they are wrong though. It happens, all right. Yeah, economists, they are not stupid people. They are like PhDs and whatnot. Went to MIT, Harvard, or whatever, Chicago, University of Chicago, or Stanford, Princeton. But they have been wrong for more than a century. Demand supply curve. It's wrong theory. Okay. What can I tell you? What can I tell you? Okay. It's just the way it is. Okay. Uh, this hot water works. It really warmed me up. I'm gonna put some more water and microwave it. Okay. Um, but yeah, we'll be back. So the so how do we calculate stress? Uh, yeah. So then how do we add them up? Yeah, yeah, yeah. It's slightly modified formula. Okay, it's we had this notation well where I gotta bring this board closer, I guess, right, so that you can see it. Oh boy, tripod walk. Oh, I gotta be careful so that it doesn't fall on me. Huh? Better? Closer and better, sure. Uh, okay, let's just talk about these two forces. How do we add them up? Okay. Yeah, it's very similar to vector summation, okay? Well, yeah, F1, oh, sorry, 1 plus 2 is equal to F1 squared plus F2 squared plus two times uh, F1, F2, absolute value cosine theta, right? Something like that, but um, not exactly. Okay. Well, we'll do one step at a time. Okay. If it's we got effect later on. Okay, when we're done with the pushing, summing, adding two pushing forces, inward stress. Later on, we gotta expand that in order to calculate both pushing and pulling. Okay, but for now, let's just think about pushing. Okay, why do we have absolute value of cosine theta? Because cosine theta becomes -1 when the two forces is 180 degrees. We have to add them up. Okay, that's why we have absolute value like this. Okay. So when theta is 0 or 180 degrees, sorry, it's f squared, okay? Then this guy becomes, cosine theta becomes, absolute value of that becomes 1. So it becomes f1 plus f2 squared. So then f of 1 plus 2 becomes f1 plus f2. Okay? So that's that. Okay, we should not subtract these two. All right, so that's the idea. Okay. So we are adding these two. Okay. The idea is, and also we are not talking about like rotation. Okay, a force that is directed like off center, you start to rotate this body. We are not talking about that yet. Perhaps later. All right. Yeah, because it's a lot. So one step at a time. Okay. Probably that's why Cauchy kind of failed. Talking about stress tensor, and I don't think we need concept of tensor. Okay. I don't think so. We'll see. Alright. If we need concept of tensor, then we'll learn it, okay? But I don't think we need concept of tensor when we talk about stress. Alright? Yeah, this thing I was making sure there's no like staple metal piece because I was microwaving. You cannot put metal in the microwave. You know that, right? Yeah, you should not put microwave or anything metallic, or aluminum foil. Yeah, you should not put it in the microwave. Okay. Yeah, I was making sure, and there's no metal piece in the staple in this tea bag, so good. Ooh, it's too hot. So, by the way, I don't like this expression melting pot. They say, "Oh, America is melting pot." That's a the worst notion there. Worst model, worst notion. Melting pot is not a good thing. Okay, we want African Americans to be African Americans. We want whites to be whites. So segregation, there's some good in there. Okay, because they preserve strong ethnicity, ethnic authenticity. Okay, yeah, in America you have Chinatown, Koreatown, Little Italy, Little Tokyo, whatever, right? Those are good things, okay, because they preserve their strong ethnicity. Okay, I don't want everybody to mix together and all become Hispanics. I don't want that. Okay, Hispanics, they're beautiful too. Okay, I'm not saying Hispanics are ugly. I just don't want everybody to be Hispanics because they all intermix, interracial marriage, everybody become equalized. Then where is diversity? You will die. Okay, we want dogs. Hey, dog, are you a dog breeder? Then we want Dalmatian to be Dalmatian. We don't want all the dogs become just one single species by interbreeding every dog. We don't want that. Okay, we want to preserve and protect the originality, authenticity, the purity of ethnic culture, tradition, language, race, human race, like white, black, brown. Yeah, we want to preserve that. Okay, that's the only way we can preserve diversity. And of course, we need to get along with each other. But melting pot, that's a bad idea. Okay. I don't know what kind of idiot came up with this stupid notion. Melting pot. My, I mean, you cook a dinner, right? Would you like to put everything in one pot and melt it? Oh my goodness, what kind of horrible, the worst food would they be? You want to have vegetable separate, mashed potato separate, meat separate. That's what you want. I mean, you don't want to put everything in one pot and melt it. That's the worst food. Okay? Oh, come on. Melting pot. My goodness, what kind of idiot came up with this stupid idea? It's satanic. Yeah, it's melting potism. That's a satanic ideology. Okay, so Satan possessed some stupid guy, I guess, or girl. I'm sorry, but yeah, whoever came up with that notion was possessed by the devil. Okay, it's the devil. Okay, yeah, it's Satan. Somebody will ask me, what is not Satan to you? Because it seems everything is Satan to you, and perhaps it's because you are the one who's possessed by Satan, and you have this eyesight, these glasses, satanic glasses, so that everything that you see looks like Satan. Hmm? Maybe you are the only one in the world who's possessed by the devil. Maybe. I don't know. Oh boy. This tea must have some alcohol in there. uh, Talking like a drunkard. Well, I like having fun, so. Okay, so. We are summing them up. This is. So this vector summation formula, well, we'll talk about traditional vector summation, okay? F of 1 plus 2 is equal to f1 squared plus f2 squared plus 2 times f1 dot f2 vector f2. This is so surprisingly, this squared, okay? Vector summation formula contains dot product in it. Okay, that's kind of surprising. I have never seen. I don't recall textbook who actually talked about this. It's kind of surprising. Okay, you have vector summation and dot product is kind of embedded inside of this vector summation formula. Okay, that is a little bit surprising. Okay, and but here we have cosine theta wrapped around this absolute value bar, 2 bars. It's not exactly dot product. Okay, so then what is this guy, geometrically speaking? Let's take a look. All right. So geometrically speaking, okay, you have two vectors. Okay, dot product. The meaning of dot product is you have f1. Okay, f1 vector right here, f2 vector here. Okay, can you see all this? Is it too far away from you? Yeah, you can see it. And theta is right here. Okay. F2 cosine theta is the projection of F2 onto F1. Okay. So this is F2. It's a vector. It's projection vector. Okay. F2 cosine theta is this guy. Okay. Now, when theta is more than 90 degrees, because cosine curve goes like this, right? Bu, bu. So this is 90 degree, pi over 2, right? Here you have pi, and here you have 3 pi over 2, which is 270 degrees, okay? So yeah, when theta is like this, it's between 90 degrees and 270 degrees, then projection, okay, F2's projection onto F1 has this opposite direction. That's why it becomes negative. Cosine, let's say cosine, what, 100 degrees, 120 degrees. Cosine of 120 degrees is a negative value. Okay. Uh, what's that value? Is it like, let's do this real quick, okay? Oh boy. Because I kind of want to know, what is cosine 30 degree? Oh boy. If 60 degree, 30 degree, cosine of 60 is, we have what, my goodness, it's been so long. I think it's like the square root of 3. Is this how it goes? I don't know. I forgot. Oh my goodness. It's been such a long time. Oh boy. It's been like very long time, okay? What is cosine of 60 degree? Okay, you have what, right triangle, right? I mean the equilateral triangle, okay? And so this is 60 degrees. Oh, I'm sorry. Okay, equilateral triangle. Let's say this is 2, 2, 2. And then it's 1. Okay, this is root 3, I think. Okay, I was confused. So 1, 2. This guy's square root of 3, okay? So cosine 60 is 1 over 2, okay? Cosine of 30 degrees is square root of 3 over 2, okay? Now, so cosine of 120 degrees is, you have 120 degrees and then you have 150 degrees, okay? Yeah, cosine of 120 degrees is minus square root minus, okay, cosine of 120 degrees is minus square root of 3 over 2. Okay, yeah, we got it. Okay, cosine of 150 degrees is minus 1/2. Okay, so Wait. I think I got it backwards. Sorry. Cosine of 150 degrees will be minus square root of 3 over 2. I think, okay? Because it's going to get negatively bigger, okay? Because cosine of 180 degrees is minus 1. Which one is bigger? Yeah, it's minus like 1.7, okay? Minus 1, yeah, this is correct. Okay, alright, so sorry, about mathematical mumbo jumbo, so yeah, just basic, I'm sorry, yeah. It's basic trigonometry stuff. I just want to remember, okay? So it's not that important, alright? So, yeah, it's very basic trigonometry, okay? 30 degree, 60 degree, blah, 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 okay? So, man, I'm getting really hot now. Oh. Um, let's get back to this, okay? So, now we are wrapping this absolute value around the cosine. What does that mean? Geometrically speaking. Basically, we are treating these two guys the same way. Okay, that's what it is. Okay, so let's say this is what 60 degree and this is 120 degrees. Okay, this guy. This is 120 degrees. Okay, and this guy is 60 degrees. Okay, we are treating them the same way. Okay, so that's what we are doing. And what is cosine of 60 degrees? Maybe this formula is kind of wrong. Okay, I don't know. That's why we are doing this kind of calculation. Okay, so, oh boy. Cosine 60 is equal to 1/2. Okay. Cosine 30 is equal to square root of 3 over 2. So cosine 60 is 1/2. Cosine 120 degrees is negative 1/2. Okay, I mean, yeah. Okay. So yeah, it makes sense. Okay, so we have to treat those two guys the same way. Okay. But does that make sense though? Should we, if two guys are pulling this mass, 60 degrees, and if two guys are pulling this center mass, 120 degrees, do they have the same effect? I don't think so. So I think this formula is wrong, okay? Because, yeah. Yeah, it's correct that if somebody's pulling this body, if two people are pulling this body in the same direction, yeah, we should add them up, right? If somebody is pulling this center body in opposite direction, should we add them up? Yes, in a way, but not the same way though. Yeah, maybe same way, okay, because if just one person is pulling this body, yeah, this body will feel the stress because this action reaction, is because inertia is going that way. We have this rock, okay, I'm pulling it toward me. but inertia of this rock is pulling this rock the other way because it's resisting. That's why inertia, but it's inertial mass. It's resisting the pull. So this rock is feeling. Two people are pulling the rock. Okay. That's why it feels this pulling. It's kind of stress. Yeah. So it kind of makes sense. If it's 0 degree or 180 degree, yeah, then we have to double. We have to add them up. But is it correct to regard these two different pulling of 60-degree pulling, two forces pulling with a 60-degree angle, and two forces pulling with 120 degrees? Should we treat them as the same kind of stress? That's the question. We're trying to understand intuitively first, okay, and come up with the right formula. I think we should treat them the same. Why? Because it's like this. Okay. We are talking about the stress this rock is feeling. Okay. Or let's say it's just me being bullied. Okay, being pulled. Okay. The two big guys. He's okay. First set of two big guys. Okay. One guy is pulling me to the right, and another big guy is pulling me with 60 degrees. Okay, so two bad guys are pulling me. One of them my ear, one of them my nose. Okay, and they twist it such that it makes 60 degrees, and they're pulling it. Okay, and then I will go that way, but the kind of stress I'm feeling is the vector summation of these two forces, okay? Tentatively, okay? And it's bad because, let's say, two people are pulling me, two bullies are pulling me. One my nose, one my hair, wow, okay? Then my body will have this inertia because I have mass, right? So two guys are pulling me in the same direction. So this we are adding up the force, stress force, because the stress I'm experiencing is the inertial force. Okay, F equal ma. Okay, so two forces adding up, there'll be huge acceleration, and my inertial mass, inertial force is the resistance force. So by pulling me by the nose, so I have mass, body mass. So I feel like one person is pulling me, and my inertia is pulling the other way because my body is resisting the change in speed. That's what inertia is, right? So yeah. Even if one person is pulling me, I'm feeling like there are two people pulling me on the opposite direction. So that's the stress. Okay. Force that's pulling me, and inertial force that's trying to, a force pulling me forward, this bully guy, okay, grab my nose, and or maybe a teacher, okay, or whoever, my boss, my parent, whoever, yeah, pulling me like this, right? And then this inertia, my body mass resisting that pulling, just because of my sheer mass, okay. So yeah, I'm feeling like pulling either way. Okay, that's the stress I'm experiencing. Okay. Boy. Okay. So stress comes from inertia. Okay, man, I'm getting really hot. We'll take a break, okay, and then we'll continue. Okay, because I'm being overheated, so I gotta ventilate the air, ventilate the room. Oh man, we, we need some room. We gotta erase something. Ah, but I don't want to buy third whiteboard. Okay, I'd rather not. I think two is enough. What do we erase? We're gonna erase that. Yeah, let's. I think it's good time to switch out the board. Okay, so ah boy. We're gonna erase this. Okay. Oh boy. Take off my jacket and. Yeah, I'm sorry about this bully analogy. I, but we have to do this, okay? I'm sorry. At least I'm putting myself on the line, so. But it's not very pleasant thing to talk about. But I mean, it's the most effective way to think about because I'm a human being, so I have nerves. I can feel things. Okay. Then who should we be pushing around? Your dog? I don't have any dogs. Okay. Moose, bear. I'm gonna push you around bear. Your dog, cat, feral cat. Ah! How about this cat that poops on my backyard? Okay, let's push the cat around. Feral cat, bad cat. Come to my yard and poops in my yard. It's not my cat. Feral cat, nobody's cat. And I don't own this cat. Then why do I have to clean after that cat? So bad cat. Okay, let's push around the bad cat. We grab the cat by the tail and start pulling. And you grab the cat, this bad cat, poop on my yard. You grab it by head. We start pulling. Oh my goodness, that's. Ew, it just sounds too horrible. Let's not do that. Animal cruelty. I don't like animal cruelty. No. Let's leave the cat alone, okay? I will crucify myself, okay? Self-sacrifice. Okay. Two guys, okay? We are doing human thought experiment, okay? You guys do that to me, okay? Uh, okay, so human experiment, okay? So no bullies, okay? It's just human experiment, okay? Kind of crucifixion experiment, human thought experiment. We are not actually doing it. Thought experiment, okay? So, okay. Here's me, okay? Yeah, I want to get crucified, because I'm a Christian. Okay? The two guys are pulling me apart. Thought experiment, okay? Don't do it for real. No. We just need to think about it, okay? Two guys are pulling me apart, okay? Here we have 180 degree, okay? This F1, F2, okay? Yeah, we are doing physical thought experiment. Next time, metaphysical. Yeah, two forces, two influential ideologies trying to pull me toward the right, toward the left, try to persuade me to become anti-gayist or pro-gayist. Okay? Now, in terms of stress calculation, yeah, we have to add them up. Okay, so I think we are kind of ready to integrate pulling and pushing. Okay. Tentatively, maybe not yet. Okay, because it gets very complex very fast. Oh boy. Because what if this F1 is this way? They need to cancel out. Okay. Somebody's pushing me, somebody's pulling me. Yeah, I'm moving with twice the acceleration. Because in terms of force, traditional vector summation, right? So double the acceleration. F equal ma. Okay? I'm going twice as. I'm moving with twice the acceleration. Okay? Somebody's pushing me, somebody's pulling me. Yeah, I'm moving very fast. In terms of stress, I'm feeling nothing. Zero stress. So it has to cancel out. Okay, that's the difference between stress force and just regular force. Okay, regular force you add them up. Stress force you have to subtract in this situation. Why? One of them is coming inward. The other force is going outward. Okay, so it's a radial vector system. Okay, it's kind of good coincidence that we started talking about radial vector system. Okay, so it's useful when we think about stress. Going outward is minus, going inward plus. So you add them up, minus plus minus, minus plus plus, yeah, zero. Okay. Then we need to come up with a nice formula to factor that in. Okay, so tentatively it's like this. Okay, so stress is equal to uh, is a scalar, okay, one-dimensional vector. It could be plus or minus, okay. Tentatively, it's like this, okay. Uh, Sigma circle, okay, is this cosine wrapped with that thing, okay. Let's just move on or keep moving, okay. If there's some error, we'll correct it later, okay. Because we gotta move on, all right. Yeah, just making sure you can see this. We actually talked about this before, okay. Whatever. If it's inward, is it inward or is it outward? Outward is then minus, okay? So we call it external, okay? It's a boolean, okay? If it's external going outward, then it's 1. If it's coming inward, then it's 0. Because it's not external, it's false, right? So, yeah, we did this before, okay? So it's kind of review. And, but ordering matters, right? Oh man, I'm getting dizzy. We have to step back because I am having some problem because we are, I'm being getting ahead of myself, I think. Okay, so sorry about my boss, but okay. Oh boy, I know it looks so horrible, but sorry. Um, let's just enumerate different scenarios, okay? Because let's do specific examples first before we generalize into a formula. Because let's make our life a little bit easier, okay? I'm taking off the second layer of my pants, okay? It's just getting too hot. Oh boy. All right. All right. First scenario number 1, okay? Scenario number 2, F1, F2, okay? Here we need to subtract. Here we need to add. Scenario number 3. Well, If somebody pushes, somebody pulls, then yeah, it should add up to 0. Okay, both of them pushing plus 2. That's a stress. Okay, our formula should come up with this kind of results. Okay, if someone is pulling apart, going outward, so it should be negative 2. Okay. Is there any other cases? I think that's it. Okay. Yeah, it has to be. Okay, so here, oh boy. Here, okay, the result should be something minus f1 plus f2. Okay, that should be the stress. Okay, here it should be plus f1 plus f2. Okay, here you have f1 minus f2. Okay, our formula should come up with this kind of things. Okay, then that's the challenge. Okay, we should which is minus f1 minus f2. Okay, oh boy, this is gonna be a challenge. Hmm. In terms of theta, here you have theta is 0 degree. Here, theta is 0 degree. Here, theta is 180 degree. Okay. Okay. Cosine theta. Cosine theta. Cosine 0 is 1, 1, minus 1. Okay? Oh boy. Oh. So far the stress vector formula that so far we have, like putting the cosine absolute value around the cosine theta, is incomplete. Okay, it's not complete yet. All right. It works when there's only pushing, then it works. But when we combine pushing and pulling, then it doesn't work. Okay, so we are expanding, we are integrating pulling now. Okay, pulling and pushing. Oh boy. So that's our next step. Okay, so by the way, treating 60 degrees and 120 degrees equally is correct, I think. Because if it's 60 degrees, yeah, they're kind of closer, you know, two people pulling me with 60-degree angle. Because I will go quite fast. Okay, so my inertial mass, inertial force is very resisting that a lot of acceleration. So I feel a lot of pressure. If somebody's pulling me in, two people are pulling me in 120 degrees, it's kind of like pulling me apart, kind of close to 180 degrees. So yeah, I'm not moving very faster, but I it's very effective torture because it's like pulling me apart in 180 degrees. It's kind of like that. So I'm going slow, but I feel this a lot of pulling. So yeah, it makes sense to 60 degrees and 120 degrees equally. Okay, by the way. All right, so we are moving on basically. Okay, from that angle stuff. Now we are thinking about pulling and pushing. Okay, combined together. And I'm experiencing some brain block. Okay, like writer's block, kind of. It's from fatigue, I guess, mathematical fatigue. Um, hmm. Yeah, looks like the sign, the negative sign or plus sign, we need to individually assign to the vectors. Okay, if it's in, out, yeah, we're gonna assign that sign. That's what this is. Because F2 is going outward, that's why we have minus here. F1, yeah, it's going inward, that's why we have plus here, plus, plus, they're going inward. It goes outward, then we have minus, minus. Okay, now we got it. Okay, so um, we have to assign that. Okay, and ooh boy. So when we calculate stress of this body being pushed or pulled, we don't really care the direction of movement. Okay, we don't. We only we are calculating the stress this body is feeling. Okay, we don't care about acceleration. We only care about acceleration to the extent of this inertial force, resistance force, because that's the stress this body is feeling. Okay, we don't care too much about direction where this guy is traveling. Okay, that's the traditional vector summation, right? We are not doing that. We are doing stress vector summation. Okay, because traditional vector summation, it's been already explored before by other people, by Newton and all the other people. Okay, we did make some contribution in that venue actually, calculation of theta, for example. Okay, so yeah, we're not going to concern ourselves with the direction of movement as a result of pushing and pulling. Okay, the only thing we concerned here is the stress this body is feeling. Okay, from pushing and pulling. So we will only calculate the magnitude of this result vector. Okay, that's the only thing we need to worry about. We don't care about what angle this body is traveling or not traveling. We don't care about that. Okay. All right. Uh, but to calculate the result vector, yeah, we do need to think about cosine theta. Okay, so let's take a break from here, okay, and let's think about dot product because we want to simplify the formula very much, okay, as much as possible, and maybe we can take advantage of dot product, okay, and we'll explore dot product in terms of cosine theta and absolute value of cosine theta, okay. So we're gonna switch out the board. We'll take a break, of course. Okay. We'll erase this, and oh my goodness, my flow is getting very messy now. We'll take a break and we'll be back. Okay. All right. Okay. Oh boy. Yeah, I'm kind of struggling a little bit. Okay. because it's a complex concept. Um, we're gonna erase all this, all right? We need to go back to the basics, okay? We can erase this too, okay? Yeah, this easy stuff. So because in Cartesian coordinate system, okay, Cartesian coordinate expression of vector, like vector is equal to AI plus BJ, okay, that kind of stuff. The dot product is very easy, okay? You just multiply each element and then you what? Add them up. It's so easy, super easy, okay? Dot product in Cartesian system is really cool stuff. It's okay. We don't even have to think about theta, cosine theta at all. That's the beauty of the Cartesian expression of a vector. Okay, dot product is so easy. We don't even have to think about angle. Okay. And we have to take advantage of that power of or simplicity of dot product being so simple. Okay. That's my difficulty here because if we define dot product as f1 dot f2, can you see this? Yeah. As f1 is the absolute value of f1 vector, okay, times f2 times cosine theta, okay. That's the traditional dot product definition. Okay, so we are trying to come up with a brand new definition. That's a dot circle, okay. Absolute value of cosine theta, okay. That's our goal. Okay. Because this thing appears in our radial vector summation. Okay. To sum up, to calculate the stress this body is feeling. Okay. And here you have what? x1, x2 plus in two-dimensional space. Okay. y1, y2. It's that simple. That's the dot product of two position vectors. Okay. Now, what would this be? That's my question. Okay. What would this look like? It cannot be the same. But we kind of thought, yeah, you know, vector I dot vector j is equal to what? 0. And vector I dot vector I is equal to 1, right? So our confusion is that then these two has to be the same, but it shouldn't be the same. That's the dilemma I'm experiencing here. Okay, and we will get to the bottom of this. And I think I need some vodka, okay, because I'm experiencing wit's end. All right, so let's relax a little bit by drinking vodka, okay? I'm experiencing stress, okay? So I want to go forward, but I'm being blocked. So I'm pushing myself against the wall, hitting the wall, you know? I'm feeling the stress now. Okay. So let's relax a little, okay? Oh boy. I mean, that's what vodka is for, right? Let's relax. I have no clue. I have no idea. Do you? Tell me. I have no clue so far. We have to think about this. What a brain teaser. Brain jerker. Oh boy. Because the main motivation is this. Let's think about I, vector I, dot product with minus vector I. Okay? That's the situation where you have I and minus I, 180 degree. So this becomes minus 1, right? But in this dot circle, it should be plus 1. No, no, no. I'm sorry, minus 1, right? Yeah, well, it should be minus 1 because we are pulling apart, right? Oh boy, boy, oh boy. Let's make some concrete examples, shall we? We are talking about 4 dots, 1 minus 1, 1 minus 1, okay? X, Y, okay? Oh, sorry. You cannot quite see that. Now, can you see this? Am I writing too small? Sorry. But I have to because we gotta preserve space, you know. You have I here, this vector, I, this vector, J, minus I, minus J, okay? 1, minus 1, minus 1, plus 1, okay? Oh boy. By the way, maybe we got it, okay? Maybe we should put absolute value everywhere. Maybe, maybe, okay? Or maybe not. Because here, this dot circle, it has to be always positive. Now, dot product in traditional sense, traditional dot products can be positive or negative because of theta, cosine theta here. So absolute value of f1, absolute value of f2 times cosine theta. So it could be positive or negative because of cosine theta. Okay? Because cosine theta is between minus 1 and plus 1. Okay? Now here, is non-negative number. The whole thing is either 0 or positive. Because of this, we put this absolute value around it. Okay? Okay? But we cannot just put absolute value everywhere because, can we? Tentatively, okay, tentatively speaking, this guy is equal to absolute value of x1, x2 plus absolute value of y1, y2. Okay, tentatively. Okay, we'll see if this is correct or not. All right. I think this is correct actually. Okay. Uh, if we define it like this, then now the question is: are these two mathematically equivalent? How do you prove that? Well, how do you prove this? This guy. How do you go about proving this? These two guys. Boy, boy, oh boy. Oh, oh my goodness, it's not gonna be that easy. Okay, so how can we algebraically, without using this shortcut of I dot j 0 1? Yeah, that's easy, right? But without resorting to that, how can we algebraically prove that? Okay, so f1 squared, f1 is position, just position vector. Okay, so on the right hand side we have square root of what, x1 squared plus y1 squared multiplied by, on the right side you have x2 squared plus y2 squared, and cosine theta. What is cosine theta? Okay, you have x1 comma y1, x2 comma y2. Now here's theta. Cosine theta, well, oh boy, oh man. Well, you have square root of x2 squared plus y2 squared. That's downstairs denominator, and the numerator is this length of this guy. Okay, and how do we express that without using theta? Because we're gonna get rid of theta, you know. I have no clue. Ooh. So this is x1, this is y1. Okay, okay. let's draw this diagram correctly, okay? Because I'm being sloppy here. We're gonna do this one right, okay? So, not very pretty. Okay. We draw a big diagram, okay? We'll do this one right. x1, comma, y1, okay? x2, comma, y2, all right? This angle is theta, okay? You have x2, here, x1, your y1, y2, okay? Yeah, it's a geometrical problem, okay? Now, we are trying to find the length of this guy from here to here, okay? The projection length, all right? It shouldn't be too hard, all right? So, we know the length from here to here, the square root of x1 squared plus y1 squared. Okay, we know that. Okay. And we know this phi as well. It's the just inverse tangent of y1 over x1. So we can get that value. And also we know that angle, we call it alpha, okay? That's inverse tangent of y2 over x2, okay? Theta is alpha minus phi, so we know that. So theta, okay? Theta is alpha minus phi, which means inverse tangent, arctangent, okay? y2 over x2 minus inverse tangent x1 over, y1 over x1, okay? Okay? So we know what theta is. Oh, gets very ugly very quick. It's getting very messy. Okay, so cosine of that. Oh my goodness. Oh, we don't want to go there. No. Maybe we have to. I don't know. I'm gonna look up trigonometric identity, okay? Because we may have to go there, okay? So cosine of that thing. What's cosine of a plus b? Trigonometric identity. Oh, I have calculus book. Maybe it's in my calculus book. Okay, let's look it up. Trigonometric identity. It has to have it. So trigonometry. Okay, cosine A minus B is equal to cosine A cosine B minus plus sine A sine B. If cosine this guy and cosine this guy, does that make it any simple? I don't think so. No. What is cosine of inverse tangent? What is cosine of arctangent? Come on. We don't want to go there. Nah, yeah. You don't kind of want to do that. Oh boy. Oh. Hmm. Well, let's just think about the other triangle right here. Okay. Let's call this angle as beta. Okay. Then um, we call this guy beta. This angle. Okay. What kind of triangle is this guy? Is this triangle and this triangle equal? Always? It can't be, right? Because if we raise the theta to be steeper angle, then it will look like that. So yeah, they cannot be equal triangle. So no. What kind of triangle is this? If theta is here, then it will look like that. Is this a right triangle? Is it? Think about rotating this line, okay? Is that right triangle? This angle. I don't think so, because what if we extend this line all the way there? You know? No, it's not always right angle. Okay. Yeah. What am I doing? I'm trying to derive this formula algebraically and also geometrically. X1 plus x2, I mean x1, x2 plus y1, y2. I want that to be equal to this guy. f1 times f2 times cosine theta, okay? It turns out it's not an easy problem to solve, okay? I'm trying to express cosine theta in terms of x1, x2, y1, y2, okay? That's what I'm struggling with, okay? It shouldn't be that difficult if you think about it. It's interesting geometry problem, okay? What we know is this. We know the length of this line is square root of x1, x2 squared plus y2 squared. We know the length of this line, okay? And we even know what theta is, okay? Because we know alpha and phi is inverse tangent of that shit, that which is very ugly, okay? So we know what theta is. So okay. So cosine theta, right? Cosine theta is then this. In a way, we can get rid of theta, okay? Because it becomes very ugly, okay? We need to prove x1, x2 plus y1, y2 is equal to this guy times cosine of tangent minus 1 y2 over x2 minus tangent minus 1 x1 over x2, okay? That we got rid of theta somehow. We are left with just 2 inverse tangent and 1 cosine, which is very ugly, okay? How are they the same? My goodness, I have no idea how to go about this. Well, let's try to work it out, okay? This guy here is square root of x1 squared, x2 squared, plus x1 squared, y2 squared, plus y1 squared, x2 squared, y1 squared, plus y1 squared, plus y2 squared, okay? That's what this guy is. Now, cosine of this, oh boy. In the trigonometric identity, cosine of a minus b is equal to cosine of a minus cosine of x minus y is cosine x cosine y plus sine x sine y, okay? So cosine this guy times cosine this guy plus sine of this guy and sine of that guy. Okay, so and somehow things should cancel out and it becomes this, and I don't know how to do that. Okay. Oh boy. We have cosine and inverse tangent. Is there a way to expand that shit? Boy. Oh my gosh. I mean, there's this Taylor series, right? Expansion, right? Let's take a look. Okay. Yeah, we can express cosine as a Taylor is a polynomial. Okay. That's called something like Taylor series, whatnot. Uh, Taylor series expansion. Oh, boy. $760. Okay. They have this Taylor series expansion. Okay. Um, okay. Well, they have Taylor series expansion of inverse tangent. Okay. So, which is really cool. We can take a shot at it. All right. So, and then they have Taylor series expansion of cosine as well. Okay. Do they have Taylor expansion of square root? Oh yeah, I'm sure they do. Well, square root. That's just it's a binomial, right? Oh boy. Yeah, representation of a function with infinite summation of polynomials. Okay. What a mess. What a mess. Such a great mess, dude. Oh boy. Yeah, I'm not having a lot of fun here. Okay. Oh boy. Yeah, mathematics not always fun. Okay. Oh boy. Oh, well. I don't want to do this really. Okay. Oh boy. I really don't want to do this. You Taylor series expansion of arc tangent, which is really cool. um. Okay. Maclaurin series. Hmm. I'm gonna look up that product, okay, in this calculus book. We're running. We only 40 minutes left. Oh, time flies when you are being tortured. No, time goes slow when you're tortured. I guess I'm having fun in a way. Okay, so that product, product. Okay, so yeah, I need some help with this. All right. Okay. The way they go about this is okay. I'm kind of getting. I'm getting some help from this calculus book, right? So yeah, yeah. I think we have enough time. Okay, so the way they do it is to calculate this guy. Okay, so all right. Yeah, we'll erase all this. I think I know how to prove this. Okay. The way they do it is this, right? From here to here, okay? It's square root of uh, from here to here, okay? x1 minus x2 squared plus y1 minus y2 squared, okay? All right? And using the trigonometric, I'm sorry, this guy from here to here, it's a length, right? Square root of x1 minus x2 squared plus y1 minus y2 squared is this guy. From this triangle, we know that is equal to what? x1 squared plus y1 squared plus x2 squared plus y2 squared, okay, minus 2 square root of x1 squared plus y1 squared multiplied by x2 squared plus y2 squared, then cosine theta, okay? Yeah, it's just a triangle, right? Okay? Because what we want to prove is x1, x2 plus y1, y2 is equal to square root of x1 squared plus y1 squared square root of x2 squared plus y2 squared cosine theta, okay? So that's what we want to prove, okay? So here you have cosine theta is equal to square root of no, we don't have square root, okay? Because in this trigonometric identity, okay, this guy squared, this guy squared, this guy squared is equal to this guy squared plus this guy squared plus minus 2 cosine theta, because when theta is 90 degree, then that's Pythagorean theorem. So it's a generalized Pythagorean theorem. Okay. Yeah. Okay. So I'm sorry if I'm going too fast. Okay. I'm just gibberishing, talking to myself, thinking out loud. But we'll review this later. Okay, because I'm running out of time. Yeah, we got it. Okay. Because here, this just I make it simpler for you later. Okay. X1 squared, x1 squared, y1 squared, y2 squared, they all cancel out. So what we have left is cosine theta becomes minus 2 times square root of x1 squared, y1 squared plus x2 squared plus y2 squared. That goes downstairs. Upstairs we have minus 2 x1 x2 plus y1 y2, okay, plus x1 squared y1 squared plus x2 squared y2 squared, okay, and by the way, we are getting very close, okay? Getting very, very close. I just made some kind of algebraic mistake, okay? Yeah, I'm sorry. It's not that. Is it? Oh boy, it's confusing. Yeah, I think we got it, okay? We don't have square here. Okay, good, good, good. Ladies and gentlemen, we got it, okay? With the help of the mathematics book, the calculus book over there, we got it, okay? We'll take a break. I'm going to explain to you what I just did, okay? We got it. Oh, it took such a long time. Oh boy. We'll take a break and I explain what I just did, okay? So, we'll be back, okay? Oh boy, we got it. Yeah, having this calculus book really helped. Oh, we'll be back. We got it. Now that we are kind of running out of time, we have to do this rather quickly. Okay, we have less than 30 minutes. Okay, where's my glasses? I was once lost, now I'm found. It's very classical hymn, Christian song. I love old school Christian song. I mean, new gospels, they're cool too. Okay. So, sorry to that I took such a long time, but we got it. Okay. I looked at the calculus book and yeah, got some idea from there. This calculus book or any calculus text, they define dot product as like x1 comma y1 dot product with x2 comma y2. They define it as x1 y1 plus x2. I mean x1 x2 plus y1 y2, right? It's wrong definition. Okay, it's wrong way to define dot product. That's not how dot product was originally defined. Dot product is a geometrical concept. The correct way of defining dot product is f1 dot f2 is equal to f1 f2 cosine theta. That's the correct definition. Okay, because dot product comes from physics. Okay, you have f1 f2, you have theta here. Okay, that's how it came about. That product came from physics. Okay, it's about force vector and displacement vector. Okay, to calculate work. Okay, you have to do the projection. Okay, W equals F times S. That product. Okay, that's where that product came from historically. Okay, so yeah, that product, this is the correct definition. Okay, this guy comes later. It's not a definition, it's an identity. It's a very cool identity, but it's not a definition. It's derived from this definition, and we're gonna derive that now. Okay, it took so long time. It goes like this. Okay, so yeah, this mathematics textbook, the calculus, it has some goods and bads. Okay, and nobody's perfect, right? So we don't fault the author. Okay, there's some correct and incorrect stuff, minor error. Okay, but yeah, that's the definition. Okay, f times y, I mean the cosine theta, f1 f2 cosine theta, that's the dot product definition. Okay, then we're going to derive why it becomes so easy and powerful, x1 x2 plus y1 y2. That's, we'll derive that. It's not a definition, we'll derive that. Okay, okay, in mathematics, all right, you have f1, we just call it a and b. Okay, to make it easier, actually we call it f1 f2, sorry, f1 vector, f2 vector. Okay, and you have theta. Okay, this guy is what, f2 minus f1. Okay, if you do add this guy together, it becomes f2. Okay, always a vector subtraction, head minus tail. Okay, head minus tail. Okay, mnemonic device. Okay, now it's a triangle. Okay, we have a formula, nice handy dandy formula, where uh, f2 minus f1 absolute value of that vector squared is equal to f1 absolute value, which is just f1, right, in our notation. I'm kind of running out of time, so that's why I'm going very fast. Okay, f1 squared plus f2 squared minus 2 times f1 f2 cosine theta. Okay, it's generalized Pythagorean theorem. When theta is 90 degrees, cosine 90 degree, it zeroes out. Okay, it's an equation that's very well known. Okay, it's a generalized Pythagorean theorem. Okay, it's one of the trigonometric identity. Okay, I don't know what it's called. We just call it generalized Pythagorean theorem, right? Yeah, it's a very well known equation in geometry. Okay. So, f1 is a position vector, okay? x1, comma y1. f2, x2, comma y2, okay? f2 minus f1 is just vector subtraction, right? So it becomes x2 minus x1, comma y2 minus y1. Okay, we're gonna just plug that in. Okay, then we will know what cosine theta is. Okay, all right, we're gonna just plug that in. Okay, that's all it takes. Because we don't like cosine theta. It's kind of like stranger, kind of, I mean, so sorry to be xenophobic, but it's kind of like alien. What is theta, man? Come on, we gotta get rid of that shit. Sorry. So, cosine theta is equal to f2 minus f1 squared minus f1 squared minus f2 squared over minus 2 f1 f2. Okay, that's cosine theta, and we just work this out. Okay, is equal to minus 2 square root of x1 squared plus x2 squared y, sorry, y1 squared square root x2 squared plus y2 squared. Okay, that's downstairs. Upstairs, the absolute value of that is kind of square root, right? Blah blah blah. So you have x2 minus x1 squared plus y2 minus y1 squared. Okay, and we put square root, and the square cancels out, right? Minus f1 squared, which is x1 squared plus y1 squared, minus x2 squared plus y2 squared, which becomes minus 2 square root of x1 squared plus y1 squared square root of x2 squared plus y2 squared, okay, over minus 2 x1 x2 minus 2 y1 y1, y2. Okay? Because x squared, x2 squared, x1 squared, it cancels out. y1 squared, y2 squared, it cancels out. Okay? So that's what we have left. So, and then this whole cosine theta thing, it becomes -2, -2, that cancels out, right? Square root of x1 squared plus y2, y1 squared multiplied by x2 squared plus y2 squared, okay? From here, okay? I'm canceling out -2, okay? x1, x2 plus y1, y2. And guess what? This guy is f1. This is f2, right? So x1, x2 plus y1, y2 becomes f1, f2 cosine theta, which is the definition of f1 vector dot product f2 vector, okay? We got it, ladies and gentlemen. Congratulations. Oh, it took forever. And we have 15 minutes left. We got this done in 15 minutes, okay? Oh boy. Whew. But we got it. All right. So that's 2-dimension, okay? 3-dimension, yeah, so it's likewise, okay, same way. But we just did this proof why this dot product can be expressed such a simple way, which is very surprising. We got rid of this sine theta shit. We don't, I mean cosine theta shit. We don't want to deal with that shit, okay? But that's the definitional term, f1, f2 cosine theta. That's how dot product is defined, okay? And it turns out, from God's grace, that we can calculate this without thinking about angle at all. It's this. So this is not a definition. It's derived property. Okay, this guy is the definition, cosine theta. Okay, but we worked it out with this using some triangle identity. Okay, generalized Pythagorean theorem. From there, we proved that it's simplified like this. Okay. So, all right. Now I'm getting hot, so I'm going to turn off the heater and all right. Now, our next step is this, okay? What if we put absolute value around here? Around cosine theta. That's our problem now, okay? Would it be mathematically equal to absolute value here, absolute value here? That's our question. Because if it is so, that's going to help us a lot. Because it's going to simplify many things when we try to calculate stress vector. Okay? That's why we went long way to calculate, to prove this thing. Because we want to find out nice handy-dandy formula of this radial vector summation. Okay, we want to put absolute value around the cosine theta, and then how would this look like? Okay, that's what we want to find out. That's our next step. And we only have 10 minutes left. We are not sure we can do it in 10 minutes. we can continue. Okay, after this, my voice is doing just fine. So let's take a shot at it. Okay. Let's take a shot at it. It's gonna be a challenge. Ooh. So we have cosine curve, okay. Cosine 90-degree angle plus x. Woo. This is x, okay. Okay. Is equal to what? Can we simplify? Can we get rid of this 90 degrees? Oh boy. Well, I guess we can use this classical. Now, instead of using this trigonometric identity like cosine 90, yeah, let's just do it. Okay, cosine 90, which is 0, times cosine, so it will be like what? Sine minus sine 90 degrees minus sine x, I guess. I think that's what it is. Okay, so because sine curve goes like okay. So yeah, it's minus sine x. Yeah, that is correct. That is correct. Okay. Why are we doing this? Because we are doing absolute value of cosine. Okay, so absolute value of cosine looks like okay, that's the absolute value of cosine. Okay. So yeah, cosine 90 degree, this is 90 degree, plus x is like minus sine x, okay? So, but then absolute value of cosine x, oh boy, it's gonna be very confusing. It's gonna be very confusing. We'll probably just continue, okay? Just keep charging. We're taking enough break, so. We need to think about only two kinds of triangles, okay? Oh boy. there's this kind of triangle. When theta is kind of like sharp angle, then there's this blunt triangle when theta is more than 90 degrees. Okay? You have f1 vector here, f2 vector here, f1 vector here, f2 vector there. Okay? What we are trying to find is this. Okay, so absolute value of cosine theta. Okay, so we are trying to say cosine 60 degrees and cosine 120 degrees. Okay, we are collecting this together. We are trying to equalize these two. Okay, now what is cosine 60 degree? Is equal to 1 over half. Okay, what are cosine of 120 degrees? Is equal to cosine 90 degree plus 30 degree, right? Is equal to minus sine 30 degree, which is equal to minus 1 over half. Okay, if we put absolute value, then they become equal. Okay, so that's what we're doing. Okay, we are defining a brand new kind of dot product here. Okay, so where f1 dot circle f2 is 2 vector. Okay, so f1 f2 absolute value cosine theta. Okay, that's what we're trying to define, and that's the definition, okay, of this radial vector summation. Okay, I mean radial vector dot product. Okay, and we want to find out some equivalent formula in a Cartesian expression, just like x1 x2 plus y1 y2. That's our goal. Okay, is it absolute value of x1 x2 plus absolute value of y1 y2? Maybe, or maybe not. That's what we are trying to find out. Is it equal to okay, that's our next project. Okay, because we are not sure if they are mathematically equivalent. We are not sure. If it is, fine. If not, we want to find then what? What is it if it's not this? Isn't it exciting? I'm excited. Okay. And it may not be very simple. Okay, it may take a couple of episodes. Okay, we don't know. I don't. All right. If we define that product like this, in a geometrical way using cosine theta, can we express as simple as this, or is it something else? Can we get rid of cosine theta and use just Cartesian coordinate values, as in just regular dot product? We want to find out, okay? Because we are not sure yet. Okay. Well, in the first blush, okay, we cannot just use that generalized Pythagorean theorem because in generalized Pythagorean theorem, you have two triangles, right? Here you have shorter length. Here you have very long length. Okay. So we are running out of time. Okay, we're gonna take a break. Okay, and we'll just continue to the next episode. Okay. All right. See you soon. Bye.